So we turn now to the strong interactions portion of the symposium of our session. And I'm so glad to see Professor Adler. I didn't get a chance to say hello before. Stephen Adler is Professor Emeritus at the Institute for Advanced Study in Princeton. Professor Adler has won many awards and done pioneering work on high-energy neutrino processes, current algebra, soft pion theorem, sum rules, anomalies, and that helped lay the foundations for our standard model. And they're the Adler zeros, the Adler-Weisberger relation, the Adler anomaly, and so on. And so, please forgive me for my own personal note. Our particle physics research at the time was so excited to write a paper with Professor Adler with all of his accomplishments, and so we were Adler number one. We had an Adler number of 1, which we were very proud of, and so Professor Adler will, in fact, now talk about both his old and new ideas about soft pions. Please join me in welcoming Professor Adler.
Okay, so I'm going to talk about soft pions, current algebras, and sum rules. An outline of my talk, I'll give some preliminaries, discuss soft pions, current algebras, which gave soft pions a lot of the power of prediction, sum rules, then some further soft pion applications, which deepen inelastic scattering sum rules, anomalies in PCAC, a brief overview of the historical significance, and finally some updates and revivals. I'll focus on a few key papers and key formulas. For more details and citations, you'll find them in the commentaries in my book, Adventures in Theoretical Physics, which is in the World Scientific Series in 20th Century Physics. Okay, preliminary. So we start from Noether's theorem. Let's start with the Lagrangian, which is a function of a set of fields phi L and their space-time derivatives partial lambda phi L. And then make a transformation. The field phi j goes to phi j plus some parameter lambda, which can be space-time dependent, times some functions gj of the fields phi. Then just applying the chain rule, the change in the Lagrangian is dl by d lambda times lambda plus dl by d partial derivative of lambda times the partial derivative of lambda. If you now define a current, J alpha, as the derivative of the Lagrangian with respect to partial alpha of lambda, so it's a sum over all the fields J, dl by d partial alpha of the jth field times gj, the function of the fields that makes the transformation. Then if you use just the Euler-Lagrange equations, a simple calculation, which is, of course, very important in its time, shows that divergence of J is minus dl by d lambda, and that's the first Noether theorem. Therefore, if L is invariant for constant lambda, so dl by d lambda is 0, the current is exactly conserved. So this makes a connection between symmetry transformations of the Lagrangian and conservation of currents. If dl by d lambda is non-zero but small, the current is said to be partially conserved. Now let's apply this to the Dirac Lagrangian. So we start with just the Lagrangian is psi bar gamma mu partial mu psi plus im psi bar psi, where psi bar is psi dagger gamma naught, and the gamma naught is going to be important. Let's first consider just a phase transformation. Psi goes to e to the I theta psi. Clearly, if theta is space-time independent, it just cancels out between the psi daggers and the psis, and L is invariant. Therefore, there's a conserved vector current, V mu equals psi bar gamma mu psi. The divergence of V mu is 0. Now let's make a transformation, what's called a chiral transformation, a chiral phase transformation. Psi goes to e to the I theta gamma 5 psi, where gamma 5 is the 5th gamma matrix that anti-commutes with the other 4 gamma matrices. So gamma 5 doesn't commute with gamma naught. It anti-commutes, but gamma 5 commutes with the product of gamma naught times gamma mu. That means that the Lagrangian is invariant only when the mass is 0, so you get a partially conserved axial vector current. If we define A mu as psi bar gamma mu gamma 5 psi, then the divergence of A mu by Noether's theorem is Im psi bar gamma 5 psi. It's a pseudoscalar density with a coefficient of the mass. If the mass is small and quark masses are small, the light quark masses, then you get a partially conserved axial vector current. So now let's come to soft pions. I've finished with the field theory preliminaries. So, soft pions came out of this famous paper of Goldberger and Treman. Sam Treman was my thesis advisor. I knew both of them very well when I was a graduate student at Princeton. And from a slightly obscure dispersion relation analysis, they eventually ended up with a remarkable formula. And I'll be referring to all the constants in the formula later on. F pi is a charged pion decay constant. Ga is a nucleon axial vector coupling constant. GR is a pion-nucleon coupling constant, and Mn is a nucleon mass. And the Goldberger-Treman relation says that F sub pi is the square root of 2 Mn Ga over Gr. And this is amazing. It's good to around 6%. In fact, more recent analysis says it's good to just better than that. I've used here the particle data group F sub pi. I'll mention my book with Dashin later on. It's the F pi in that book divided by M pi squared. Okay, this was in 1960 reinterpreted as either a partially conserved or pion pole dominated axial vector current. So here I'm going to shift to the Gell-Mann notation. The axial vector current 1 plus I2 isospin component is this script F 1 plus I2 5 lambda. And what the PCAC hypothesis says is the divergence is approximately a constant times the creation operator for a charged pion or the annihilation operator for a negatively charged pion, creation for a positive charged pion. And the constant is the square root of 2 MnGa over Gr at off shell at pion mass 0, which is approximately G square root of 2 MnGa over Gr, and that's F sub pi. So this is a reinterpretation in field theory language of why you might expect the Goldberger-Treman relation. This was done by many people, by Nambu, by Bernstein, Fubini, and Gell-Mann, and Turing, Gell-Mann and Levy, Bernstein, Gell-Mann, Michel, and Cho in China. People learn about that much later, all in the year 1960. Okay, some early applications. There's an important paper by Nambu and Laurier in 1961, who first, in generalizing some ideas, I guess, of Kinoshita, gave soft pion theorems. They defined a chirality as the nucleon plus the pion axial charge. So it's the integral of the fourth component of an axial current. And then they showed that the in-to-in matrix of the chirality would be the out-to-out matrix of the chirality if the time derivative of the chirality is 0. And from this, they applied this in particular to pi plus nucleon to 2 pi plus nucleon, to try to relate the production cross-section for 2 pions with 1 pion soft to the cross-section for pi nucleon scattering. And it worked to within about a factor of 3, but not better. That was probably one of the reasons why this didn't really catch on at the time. There wasn't follow-up work. The other was that there was an undetermined coupling constant, an undetermined renormalization constant relating their chirality to the axial, which was not determined in their analysis. I later showed that this was just G sub A. So there were some pieces that were a bit obscure, and this paper, which was the predecessor of all soft pion theorems, kind of languished. The other application that was before soft pion theorems became prominent was a paper I wrote relating called Tests of the Conserved Vector Current and Partially Conserved Axial Vector Current Hypotheses in High-Energy Neutrino Reactions. At that time, CVC was already a popular acronym. I introduced PCAC because I thought the partially conserved axial vector current should be given another catchy acronym to popularize it. And the idea here was it relates the cross-section for a neutrino plus any target alpha to lepton plus beta with a forward lepton to the cross-section for pion plus alpha to beta. The reason that works is that when the lepton is forward, if you can neglect the mass of the lepton, the form momentum transfer between the neutrino and the lepton is 0. So that's like a massless pion, or a 0 mass pion. And so nu L bar, in other words, a k squared equals 0 or forward, is like a pion by PCAC. So you get a proportionality between this differential cross-section and the cross-section for the purely strong interaction process, pi plus alpha to beta. Now this is a hard experiment to do, so it's only tested decades after the paper and decades after all of the soft pion work. Okay, the first indication beyond the Goldberger-Treeman relation that soft pions can be a precision tool. At the time I started on looking at PCAC, Treeman rather said there's only one number, the Goldberger-Treeman relation, but soon there were going to be more numbers. There's a paper I wrote partly, I did it while at Princeton, but wrote it up with Phil Anderson's permission. I took some time off to write this up when I was working at Bell Labs that summer after I got my PhD. It's called Consistency Conditions on the Strong Interactions Implied by a Partially Conserved Axial Vector Current. And this came out of my study of weak pion production. By manipulating some of the amplitudes, I found that PCAC implied the following relation, that the symmetric isospin pion nucleon scattering amplitude, A pion plus, at 0 energy and momentum transfer is equal to GR squared over MN, the pion nucleon coupling constant squared over the nucleon mass. And by a dispersion relation analysis using the pion nucleon measured phase shifts, I showed that this is good to about 10%. The reason this fits in the same framework is that here you have pi plus n to pi plus n. When one pion is soft, that gets related to pi plus n to n, which is just a coupling constant. So this is the simplest case of a soft pion theorem, where you take one soft pion out and relate it to the reaction without the soft pion. I also showed in the same paper that if you look at the pion-pion reaction, again with the fourth pion off shell, the corresponding answer is 0. This is the origin of the so-called Adler zeros. In the second paper, I worked out the general external line insertion rules. This really relied on the kinematics of weak pion production. In the second paper, and a lot of dispersion analysis just to establish that the relation worked. In the second paper, I gave the general external line insertion rules, and so you start with A to B with a soft pion. That can be related to A to B without the soft pion. And when there are nucleon lines, or in general baryon lines, lambda, sigma, whatever, there's a non-zero insertion. But for pion lines, just because there are 3 pion vertexes 0 by the pseudoscalar nature of the pion, there's a 0 insertion, and that's the origin of the zeros. Okay, now we come to current algebras, because this still is just looking at PCAC by itself. There's a famous paper in the first volume of Physics. Physics was a journal that Phil Anderson started. It ran, I think, for 3 volumes, and it was discontinued. But it's now been reprinted in the PROLA database of the American Physical Society. So you can find all the issues there and download the papers. This is Gelman's paper, The Symmetry Group of Vector and Axial Vector Currents. And here I'm using his notation. He defined a vector charge as the integral of the vector fourth component, and an axial vector charge as an integral of the axial vector current fourth component. And then the first 2 relations in his paper are just a statement that Fj and Fj5 are SU3 octets. So Fi, Fj is I, Fijk, commutator of Fi with Fj5 is I, Fijk, Fk5, where the I and these are now SU3 indices, and this just says that they're octets, because the vector charge is the SU3 generator in SU3. But then he introduced something revolutionary. He said the commutation relations of the operators Fi5, in other words, the axial vector charges, close the algebraic system by giving commutator Fi5 with Fj5 is I, Fijk, Fk. The 2 axial commutators, gamma 5 squared is 1, close back into a vector charge. This he got by simply abstracting from the simplest quark model. But this is revolutionary because it had very important consequences. Now, in the same volume 1, an important tool for exploiting this was given in the paper Renormalization Effects for Partially Conserved Currents by Fubini and Furlan. And what they did was to take the isospin raising vector charge commuted with the isospin lowering vector charge. That gives the isospin neutral vector charge, which by conserved vector current has a matrix element of 1, so you know what it is. And then they took the novel ingredient was, instead of taking this matrix element at rest, they took it in the infinite momentum frame. They said, let's take it with a nucleon of momentum p, and let p sub z go to infinity. which gave a nice kinematic simplification, but in the axial vector case is absolutely crucial. Now, let me mention also that in the same volume 1 of physics, there's also the famous Bell paper on the Bell inequalities. So it's a really classic volume. Well, now the logical thing, knowing both the Gelman current algebra and the Fubini-Furlan idea of the infinite momentum frame, was to apply the same thing to axial vector charges, which was what was done by me and by Bill Weisberger. And you simply take the same commutator, but with the F's vector replaced by F5 raising, F5 isospin lowering axial vector. That closes into the neutral vector current charge, which has got a matrix element of 1. You take the p to infinity limit, and that's important because the axial vector charge matrix element between nucleons at rest is 0 by parity, but is not 0 in the infinite momentum frame. So you get something non-trivial. And when you introduce a time derivative upstairs and a denominator downstairs and use PCAC, you end up with the following remarkable sum rule, that the axial vector coupling constant in nucleon decay GA squared is 1 plus f pi squared times numerical constant times the integral from threshold to infinity of factors w dw over w squared minus mn squared. This denominator comes from putting the d by dt upstairs to get PCAC, times the difference of the pi plus proton cross section at energy w minus the pi minus proton cross section at w. This gives GA is 1.24, experiment now is GA is 1.272. So we see we're now beginning to get some good precision from PCAC. Sam Treatman said, well, now there's a third number. See, the consistency condition was a second number, now there's a third number, and that was then got people interested. In a later paper where I wrote the PhysRev paper, when you wrote a letter in PhysRev letters in those days, you were supposed to write a follow-up longer paper in PhysRev. I don't think that's the rule now, but anyway, there was a longer paper in PhysRev where I also derived a pi sum rule. One is f pi squared times the corresponding integral of the pi minus pi plus cross section minus pi plus cross section. And I showed the data was very imprecise because you didn't have pion scattering cross sections then. But with what you knew, it was clear you needed a large I equals 0 S wave pi cross section to saturate this sum rule. I also then combined the pi plus nucleon scattering with that forward lepton theorem to convert this sum rule into, and its vector analog, into sum rules for forward lepton inclusive neutrino nucleon scattering. So the forward lepton theorem, which says that forward lepton scattering looks like pion scattering, combined with the Adler-Weisberger sum rule, then leads you into deep inelastic or inclusive cross section. It's not at deep inelastic because it's k squared equals 0, but it leads you to inclusive neutrino nucleon scattering sum rules. Okay, well then there was a flood of papers after this because there were 3 numbers. It looked like you could really get precision results from the combined ideas of PCAC and current algebra. Just to mention a few of the more prominent ones, Callan and Treatman gave a relation between k to pi L nu and k L nu. Weinberg analyzed k to 2 pi L nu and showed the importance of pion pole terms. And the pion pole terms also enter into pi n into 2 pi m, which is one of the reasons why Nambu and Luria didn't get a good answer in their initial comparisons with experiment. Weinberg also gave a discussion of pi scattering lengths and multiple pion production. These papers are all reprinted in the book I put together with Roger Dashin, Current Algebras and Applications to Particle Physics, Benjamin, 1968. There's also a nice discussion in Sidney Coleman's collected lectures. Chapter 2 is on soft pion theorems, the book Aspects of Symmetry, probably many of you have looked at because it's marvelous lectures on many different foundational ideas in particle physics. Now, up to this point, I never really heard of the idea of pion theorems as being an aspect of Nambu-Goldstone bosons. That, to me at least, first appeared in the papers chiral SU3 cross SU3 as a strong interaction symmetry by Dashin, and a somewhat similar paper, well, a different paper on the same idea by Gelman, Oakes, and Renner. These are both important papers generalizing the soft pion theorems to the full SU3 octet, and they emphasize the distinction between symmetry breaking of the axial charge by polarity doubling as opposed to symmetry breaking by having a massless Goldstone boson appear, or an almost massless boson. And then there was a development by Weinberg and Callan, Coleman, West, and Zimino of chiral Lagrangians as generating functions for all of the soft pion theorems. Okay, now let me turn to deep inelastic scattering sum rules. As I noted, combining the forward lepton theorem with the GA sum rule, you were led into a sum rule for deep inelastic scattering in the forward direction. When I was at CERN in 1965, Gell-Mann urged me to try and generalize it to non-forward scattering. And whoops, hold on, now I've gone back. Okay, here we go. And when I was sitting at a breakfast table at Lake Garda, where I'd gone to visit my wife's cousin, they went off on an expedition. I finally got all the kinematics to come together. And what came out is this sum rule, and a somewhat different notation from the one I use then, that 2 is equal to the integral d nu, where nu is the energy transfer between neutrino and lepton, of W2 nu bar P of Q squared nu minus W2 nu P of Q squared nu. Notice that this is, you've integrated out the nu, but it's independent of Q squared, which means that if the contributions are all just a form factor squared, that couldn't work. But that's what you get from all the low-lying resonances. And in particular, the limit as E nu goes to infinity of d sigma by dq squared for nu bar P minus d sigma by dq squared of nu P is simply a constant, G Fermi squared over pi. Well, neutrino experiments are hard to do, but Bjorkane used isospin rotation to convert this to something that could be tested at SLAC, where they do electronic scattering experiments. So his relation was the limit as the electron energy goes to infinity, the sigma for the proton plus on the proton plus neutron target by dq squared, this is electron scattering, is greater than 2 pi alpha squared over q to the 4th. The q to the 4th is just the virtual photon propagator. So you see again, when you multiply back by q to the 4th, there's a hard kernel inside. And the origin of that hard kernel was explained in another famous paper of Bjorkane, Asymptotic Sum Rules and Infinite Momentum, where he introduced a scaling idea that nu times W2 of Q squared nu should approach a function of x, where x is the scaling variable or ratio Q squared over 2mn nu. And you can, applying this to the sum rule, you can see that then the Q squared drops out, and now you can get a hard kernel independent of Q squared when you do the integral. Okay, let me now come to anomalies. This is a big subject. There's a paper that I wrote, and a paper that called Axial Vector Vertex of Spinor Electrodynamics, and a paper that Bell and Jack Heath wrote called the PCAC puzzle pi naught to 2 gamma in the sigma model. And the combined wisdom of these two papers led to the following formula, which is in an appendix of my paper. It says that if you want to do PCAC in the presence of electromagnetism, you start with the original piece. Divergence of the axial current is F pi over the square root of 2 times the phi neutral pion field. But if for the neutral piece, you have to add something proportional to the anomaly. And it's got a well-defined coefficient. It's S, where S is the sum of axial currents times hadronic constituent charges squared times the usual anomaly, alpha over pi, F times F dual. Now, if you apply this to the calculation of pi to 2 gamma decay, there's something called the Sutherland-Veltman theorem, which says that the left-hand side for kinematic reasons actually vanishes. So if you didn't have this piece, you can conclude that pi naught decay to 2 gamma vanishes, but it doesn't vanish. Once you know Sutherland-Veltman and the anomaly corrected PCAC, you find that the pi to 2 gamma decay is entirely determined by the triangle anomaly with a coefficient that counts quark charges. And in particular, the pi naught to 2 gamma matrix element for charge 2/3 and minus 1/3 quarks was a factor of 3 too small, which had consequences later on, as I'll say in a minute. Now, in order for this to make sense, you have to know that higher order strong interaction corrections don't mess the counting up. And that's where this paper I wrote with Bill Bardeen came in, absence of higher order corrections in the anomalous axial vector divergence equations. S has no higher loop corrections, so it does count quarks. The anomaly coefficient is not renormalized by radiative corrections. Okay, let me now survey very briefly the historical significance of all this. First of all, the fact that the current algebra and PCAC program gave a lot of results that agree with experiment was indication that quantum field theory was the right thing to do, and not the reciprocal bootstrap. When I came into the physics and came to conferences, every conference would have a Mandelstam diagram on the board at the beginning, and the lure, the mantra was that hadronic physics would be explained by a reciprocal bootstrap. And after the success of PCAC and current algebra, that idea faded. It was clear that field theory really had a future, despite the fact that the strong coupling constant was too big to do perturbation theory. This is sort of an indirect approach. You are taking certain structural properties of the strong, what was hoped to be the strong interactional Lagrangian, and derived relations which were found to be true, and that hinted that there was a field theory with a Lagrangian underneath. PCAC showed that the strong interactions have an approximate chiral invariance, which we now understand to be due to the fact that the quark masses, the light quark masses, are very small compared to the QCD scale. The success of the Gell-Mann current algebra indicated that there's a non-abelian or Yang-Mills gauge structure of the electroweak sector. The deep inelastic sum rules and scaling led to the reality of quarks, and the anomaly calculation of pi naught to 2 gamma led Bardeen, Fritsch, and Gell-Mann to introduce a color tripling of quarks. So each of these little bits of theory, these nice theoretical formulas, had important implications as hints of what the underlying structure should be. For an excellent book-length discussion, see this book by Tianyu Cao, From Current Algebra to Quantum Chromodynamics, A Case for Structural Realism, Cambridge University Press, 2010. Okay, so finally let me come to some updates and revivals. About a decade ago, I learned that Paco Indurain, who unfortunately died not long after we did this work, had very accurate pion scattering sum rules obtained by careful dispersion relation analysis. So I wrote to him and said, well, can we go back and look at this pion scattering sum rule? And that led to a paper in which this was done, and it led to an updated evaluation of both the Adler, Weisberg, and pi scattering sum rules and of the Goldberger-Triemann relation. These were shown to be better than 6% with current data, and the Goldberger-Triemann relation to like 2.3%. The other thing I got into recently was I wrote an article for the Scholarpedia about the deep inelastic sum rules, and I updated the derivation there using the full 3-family Kobibo, Kobayashi, Mascala matrix for weak mixing. So some of the funny things in my original paper where there were sine squared of the Kobibo angles, when you put in the full mixing matrix, those go away and the coefficient is just 2 in front. You don't get the sine squared theta c's entering. Okay, now revivals. Well, the most prominent revival of these weak pion ideas is probably, and soft pion theories, is probably the axion. It's a very light pseudo-Nambu-Goldstone boson. So it's a neutral pseudoscalar pion analog that arises, as shown by Weinberg and Wilczek, from spontaneous breaking of the Peccei-Quinn symmetry, which was introduced to solve the strong CP problem. And now that people so far have not found WIMPs, weak interacting massive particles, as dark matter candidates, a lot of prominence is being given to looking for axions or similar very light pseudo-Nambu-Goldstone bosons as a light dark matter candidate. Another revival, it's faded a bit, but I think it may well come back, is the idea that the Higgs boson itself may be a Nambu-Goldstone boson, a pseudo-boson. This was introduced by Susskind and Weinberg with the catchy name Susskind of Technicolor. Now little Higgser versions of it, but now that people haven't found supersymmetry as an explanation for the hierarchy, I suspect that there will be more activity again on the idea that the Higgs boson may be a composite. Okay, so these ideas are currently active in a different guise. Thank you.
So we have a chance for some questions, please. And the microphone is ready. Anybody have? You did such a wonderful job of going through the whole thing you just made. But by the way, I have to tell you that there's one thing that you didn't mention, but that it just seems to be really a big part of You know, you've seen these developments when people are looking at massless amplitudes, especially tree amplitudes, BCJ kinds of things, where they find that the number of independent amplitudes are far fewer, smaller than the number of Feynman diagrams. Mm-hmm. And in doing all of that, so they have these symmetries and so forth, but what they're doing is applying your zeros.
This is soft theorems again reappearing in that guy's, yeah.
Yeah, and they're getting these, I don't know, to me they're mysterious symmetries that they see for, general amplitudes.
Yes.
But it's really highlighted by your zeros. Mm-hmm. And I was just wondering, and were any people in the audience who sort of have followed that, that's a really a big thing where your constraints and the understanding of your zeros have become, again, very important.
Yes.
But anything else?
A question over there?
Oh, there's a question.
Helen, yeah.
It's not really a question or a remark.
Yeah, I guess I don't need this.
So, as you say, this work is part of the basis on which the whole standard model, I would say strong interaction, but also the standard model picture of weak currents developed, right?
Yes.
And I think it's also fair to say that this work is also a basis for the whole industry of effective field theory.
Yes, that's right.
All the soft effective field theory theorems come out of this basis. So although in the 60s it seemed that a lot of pieces were muddling around, and as you say, there were pieces which have disappeared totally, there was a lot going on that was forming the basis of the understandings that then allowed us to move into the standard model theory. And I just want to say that for the people who weren't around at the time and don't see the connections, because it's very formal, your presentation of the math. But in fact, the things we were learning with current algebra, with soft pion theorems, were really important pieces to understand what was going on enough to be able to develop the standard model, I would say.
And the idea of effective field theory is still very relevant. Suppose, for example, just as taught, since we don't see supersymmetry, suppose a hierarchy is explained by having an intermediate mass scale where everything that we see, the quarks, leptons, and the Higgs, are all composites. Then the standard model would just be the effective field theory for that higher level of ground unification and compositeness. And if the scale is high, it may be inaccessible experimentally just for practical reasons. Suppose the scale is not 100 TeV, which the Chinese might build a machine for, but 1,000 TeV. There's no reason why it couldn't be, or 10,000. So we have a conundrum of trying to go from the clues we have now to the next level, possibly in the absence of experimental input. But there should be enough clues in what we have to do it. It's going to be tough, but we have a very good effective field theory called the standard model below, say, 1,000 TeV. And then the question is, what's beyond?
If I can add just something that it was just always so amazing, and I'm happy to, all these years later, to mention, in that anomaly business, and the anomaly has been a cornerstone discussion of all the different theories that people have tried to develop, where they have to eliminate it for renormalizability, and it's just been an important constraint. But what I have to tell you, what was truly amazing was that when you came out with your paper and you get this number out of just doing the bare triangle graph, lowest order triangle graph, this is a perturbation theory discussion, and showed that all the higher order corrections were zero.
And Bob collaborated with me in a paper on that.
That was why I told it to him.
A student of Ken Johnson's wrote a paper claiming to show that in the massless Fermion case, the anomaly is non-renormalized. Well, then there are hideous infrared divergences. And with the help of Bob's calculational skills, I remember sitting down in our porch in great heat finalizing the paper. It was a long, bitchy calculation, but the result was that when you do the infrared stuff right, the anomalies are 0. The anomaly corrections are 0. It was a very hard calculation.
But the point was you had already shown it, and it was really, you may recall there was a paper that was wrong.
But it was necessary to rebut that, and that was a tough calculation.
Right. But it was an amazing result, and it survives correct to this day. So please join me in thanking Professor Adler again.